A Hall effect sensor is a solid-state electronic device that measures a passing magnetic field and outputs a changing voltage based on the strength of that magnetic field. Using this principle and the class prompt of nature, our group decided to build a cyclocomputer to log total distance traveled and current speed of a bicycle. A magnet would be attached to the spokes of one of the bicycle wheels and the sensor attached to the bicycle frame. As the wheel rotates, the magnet would pass by the Hall effect sensor, creating a change in voltage that we could then measure using an Arduino. By measuring the wheel's diameter and building a simple counter, we could use fairly simple math to track the number of wheel rotations and convert this to total distance traveled. With the addition of a timer, we could measure the length between voltage fluctuations, giving us speed. The Arduino would then output this data to an LCD display to give useful feedback to the cyclist in real time. The specific sensor we were issued, the AH49E, has a resting voltage of approximately 2.5 volts with no magnetic field present. When a magnet passes by the sensor, the voltage either increases towards approximately 4 volts or decreases towards approximately 1 volt, depending on the strength and polarity of the magnet. Luckily for us, the AH49E sensor features integrated circuitry with low noise output, eliminating the need for physical filtering and amplification. We were able to simply connect the sensor to the Arduino and start measuring voltage fluctuations. As the sensor experienced slight voltage fluctuations from no distinct cause in the real world, we built a digital band reject filter into the code. This way, the Arduino would only count a revolution when it read a voltage above or below a certain threshold, which we tuned specifically for the magnet being used. We attempted to make the filter band as wide as possible to reduce error, while still ensuring the system would not miss a count. By the time we demoed our project, we were confident that this filter was providing accurate results. Our sampling frequency was both simple and yet the most time-consuming part of this project. We decided to sample each time the program completes one scan of the main loop. We believe that the Arduino should have been able to scan thousands of times per second, which would be significantly faster than necessary when determining the wheel speed of a bicycle. Because we had extremely limited coding experience, we did not realize that the original code we wrote was extremely inefficient. When the wheel speed was slow, it seemingly worked as it should. However, once the wheel speed increased above a certain threshold, the program scan time was taking longer than a single wheel rotation, causing our system to miss counts. This was giving us extremely confusing results, which we were not able to interpret correctly on our simple benchtop test rig. The issue did not become apparent until we attempted to confirm the calibration of the system on a lathe with precise spindle speed control. With precise control, we realized the issue was not intermittent as we had originally thought, but noticed it began to occur consistently above roughly 180 RPM. At this point, we used Google Gemini to analyze our code, and it pointed out several ways we could vastly improve the efficiency of our code. We had thought the program scan time took microseconds, when in actuality it was taking milliseconds. After making recommended changes, we found the Arduino was consistently sampling at speeds up to 500 RPM without missing counts, and likely would reliably sample even faster than that. Well, we did achieve our initial goal of building a self-contained cyclocomputer that would give real-time, accurate feedback to the user. There are several aspects of our design we would try to improve upon given more time. To begin with, the physical design aspects of our project would likely not survive extended daily use on a bicycle. The housing of our Arduino is not waterproof or shockproof, and the physical size and weight of the unit we assembled is much too big and heavy to be of much practical use to the type of cyclist that would use a system like ours. We were limited by the constraints of our kit, though we did our best to assemble something practical from the parts we had available. The wiring and sensor itself seems somewhat delicate, and the ergonomics could definitely stand improvement, although again, this could be mitigated with more time and capital to invest in design. Another feature we would investigate with more time would be an acceleration function built into the code. We did experiment with one towards the end of the project, but found it increased our code complexity and scan times somewhat significantly, and it also did not provide any practical, useful information to the cyclist. For these reasons, we removed it from our final product, though there may still be some use case for recording and calculating this data that we were just not seeing at the time. In conclusion, our team is happy with our final prototype, and we feel we have achieved the objective we set out to accomplish at the beginning of the semester. Special thanks to the authors at Arduino Docs, the Arduino.cc forums community, Google Gemini, and Amanda Gussai at Instructables.